A collision on the surface of one of our solar system's giants. The implications of this discovery stretch far beyond Neptune itself, forcing a re-examination of the dynamic and sometimes violent nature of planetary systems. Before we start, smash the like and subscribe buttons for more updates. The detection began with an anomaly. The James Webb Space Telescope was conducting a scheduled observation of Neptune's atmospheric activity, part of a long-term mission to study the ice giant's seasonal changes. At first, the data seemed confusing. Bright spots appeared unexpectedly along the planet's surface. Bright, chaotic patterns of thermal and visual disruption where normally there would be the smooth swirling bands of its methane-rich atmosphere. Webb's infrared instruments revealed abrupt spikes in heat signatures concentrated around a specific region of Neptune's atmosphere. These were not minor fluctuations. The scales involved were enormous, suggesting an energy release that could only be explained by a monumental impact. Drawing from the immense detail Webb can provide, researchers quickly pieced together what had occurred: a massive celestial object, possibly a rogue asteroid or even a minor dwarf planet that had strayed from its orbit, collided head-on with Neptune. Estimates based on the infrared analysis suggested that the impacting body could have been tens of kilometers across, traveling at velocities that defy everyday comprehension. At such speeds, the energy of the collision would rival the combined arsenal of the world's most powerful nuclear weapons millions of times over. The force unleashed by this encounter was enough to pierce Neptune's upper atmosphere, momentarily disrupting the planet's deep-layer weather systems and sending shockwaves across its ethereal blue clouds. This was not just a simple event of debris meeting atmosphere. It was an astronomical ballet of cause and effect that reached into the very identity of Neptune's existence. The turbulence visible after the impact revealed not only the layers of Neptune's atmosphere in unprecedented detail, but also hinted at the presence of deeper hidden processes at work within the planet's interior. Scientists marveled at the sudden upwelling of material from lower atmospheric layers, thrust into visibility by the violent disruption. This rare glimpse beneath Neptune's typically inscrutable exterior offered an invaluable opportunity to study its chemical makeup, which until now had remained largely speculative. Beyond the awe of the collision itself, the event raised significant questions about the stability of the outer solar system. It had long been assumed that the regions around Neptune and Uranus were relatively quiet, disturbed only by slow, gradual changes over millions of years. The detection of such a massive impact suggests otherwise, that even in the cold, distant reaches of the Sun's gravitational influence, dynamic and cataclysmic events still unfold. Webb's discovery implies that the Kuiper Belt, the massive ring of icy bodies beyond Neptune, may be far more active and chaotic than previously thought. The notion that large objects could be dislodged from the belt and hurled inward at high speeds opens a Pandora's box of possibilities regarding planetary defense and the ongoing evolution of the solar system. The sheer size of the object that collided with Neptune hints at forces at play far beyond the planet itself. Perhaps gravitational interactions with unknown massive bodies lurking at the edges of the solar system, the theorized Planet 9 or even rogue stars passing nearby, could occasionally disturb the delicate balance, sending massive objects hurtling inward. If such disturbances are more common than previously suspected, it means that all planets, including Earth, are periodically exposed to catastrophic impacts from deep space, though at vastly differing timescales. Neptune's magnetic field, already one of the most unusual in the solar system due to its extreme tilt and offset center, may have also been affected. Early readings post-collision indicated temporary disruptions in the planet's magnetic environment, offering another line of inquiry for scientists eager to understand how external forces can shape planetary magnetospheres, a subject of critical importance for understanding planetary habitability in exoplanetary systems. Moreover, the collision on Neptune presents a new opportunity to rethink the long-term geological and atmospheric evolution of ice giants. If impacts of this magnitude occur even once every few million years, they could be a major driver of atmospheric chemistry, internal heat distribution, and even rotational dynamics. Perhaps features observed on Uranus and Neptune, previously attributed to slow internal processes, are in part the scars of ancient collisions that, like this one, dramatically reshaped their histories. James Webb's ability to detect the collision and observe its immediate aftermath with such clarity marks a historic leap in humanity's ability to monitor and understand the solar system. Previous telescopes would likely have missed such an event entirely or only captured its fading remnants. Webb's sensitivity allowed scientists to observe thermal and chemical changes in real time, to chart the dispersal of debris clouds, and to model the energy propagation through Neptune's dense atmosphere. This collision also rekindled a sense of cosmic vulnerability. For all the technological and scientific advances humanity has achieved, this sudden violence unfolding on a distant planet reminds us that space remains an unpredictable, dynamic frontier. The same processes that shaped the early solar system, chaotic collisions, gravitational perturbations, and violent transformations, are still at work today. Earth's relative stability may be more of a fragile gift than a guaranteed constant, a realization that adds urgency to ongoing efforts to understand and perhaps one day prevent catastrophic impacts closer to home. There is a broader philosophical dimension to consider as well. Events like this impact are stark reminders that planets, stars, and entire systems are not permanent fixtures but act in an ever-changing cosmic play over vast time scales. Planets can be shattered, atmospheres stripped away, orbits changed beyond recognition. Neptune's collision demonstrates that even the mightiest planetary bodies are subject to the whims of fate, mere moments away from dramatic transformation by forces larger and older than humanity itself. The scientific world now finds itself at the precipice of a new era of discovery. Driven by the capabilities of the James Webb Space Telescope and spurred by the questions raised by this collision, there will be countless follow-up observations, theoretical papers, and heated debates as researchers scramble to understand exactly what happened, how often it happens, and what it means for the broader narrative of the solar system. Questions about the origin of the impactor, its composition, and its journey through the solar system will fuel years of inquiry, potentially unlocking secrets about the birth and ongoing life cycle of the planetary family to which Earth belongs. In the weeks following the detection, simulations were run using supercomputers to reconstruct the collision. These simulations suggested that the object likely fragmented upon impact, sending high-velocity shards deep into Neptune's interior, perhaps even altering the planet's internal structure in minor but measurable ways. If true, then every layer of Neptune's atmospheric and magnetic personality may now bear the fingerprints of this violent encounter, encoding the story of the impact in ways that future generations of astronomers will continue to unravel. On the observational front, the debris cloud thrown up by the impact presented an opportunity to study the physical properties of Neptune's atmosphere under extreme conditions. The expanding shockwave from the collision revealed complex patterns of atmospheric movement, helping to refine existing models of how gases behave under the planet's frigid and high-pressure conditions. This knowledge is not only valuable for understanding Neptune itself, but also for interpreting data from distant exoplanets that may share similar compositions and climates. One of the most tantalizing possibilities raised by the event is that such impacts could play a role in the mysterious phenomenon of Neptune's heat. For decades, scientists have puzzled over why Neptune emits significantly more heat than it receives from the Sun. Perhaps periodic infusions of energy from massive impacts contribute to maintaining its internal heat budget. If so, it means that what was once thought to be a slow, static cooling process is instead punctuated by sudden injections of violent energy, reshaping not just the outer layers but the planet's very thermal heartbeat. For planetary scientists, the impact was a rare, perhaps once-in-a-lifetime chance to observe the complex chain reaction triggered by a cosmic collision in a real-world environment. The lessons learned will ripple outward into many fields, from understanding planetary system formation to refining models of atmospheric chemistry, to preparing for the remote possibility of defending Earth from future impacts. The collision on Neptune becomes a microcosm for understanding how chaos, destruction, and creation are intricately intertwined in the universe's grand design. The James Webb Space Telescope has already revolutionized the way humanity sees the cosmos. But by capturing this event, it has demonstrated a power even more profound: the ability to witness the solar system's raw, unpredictable vitality in real time. As the data continues to pour in, each new finding adds another brushstroke to the vivid, chaotic painting that is Neptune's story, a painting made not in calm, predictable lines but in the furious, incandescent strokes of cosmic violence. This singular event underscores a fundamental truth about the universe, that it is not a finished sculpture, but a living, breathing thing, constantly reshaping itself through the dance of gravity, collision, and evolution. Neptune's recent collision, unveiled by Webb's unfailing gaze, is not an isolated event but part of an ongoing saga stretching back to the solar system's fiery origins, and stretching forward into an unknown future. The stars may seem still from a distance, the planet serene, but up close, the universe tells a story written in the language of fire and motion, of chance and inevitability, of creation through destruction. And in that story, Neptune's recent wound will forever be a chapter, a fleeting yet monumental testament to the restless heart of the cosmos. Confined to our own solar neighborhood. After its historic encounters with Jupiter and Saturn, Voyager 1's trajectory took it beyond the grasp of the Sun's dominant gravitational pull. In 1990, just before its cameras were powered down to conserve energy, the spacecraft turned back one final time to capture the iconic pale-blued image, an ethereal photograph of Earth suspended in a shaft of sunlight, barely a pixel in size. This single frame, so small yet so profound, would come to redefine humanity's perspective of its place in the cosmos. As Voyager 1 continued on its journey into the interstellar medium, scientists back on Earth marveled at the data still trickling in. Even decades after launch, its instruments, though aging, were still functioning, sending back crucial information about cosmic rays, magnetic fields, and plasma waves in regions of space no other human-made object had ever ventured. In 2012, a milestone long anticipated finally arrived. Voyager 1 crossed the heliopause, officially leaving the protective bubble of our Sun and entering interstellar space. It became the first spacecraft in history to do so, breaking boundaries once thought unreachable. This achievement wasn't just a triumph of engineering, it was a testament to the enduring spirit of exploration. The spacecraft, launched when disco ruled the airwaves and rotary phones still hung in kitchens, had outlasted presidents, wars, and even the lifespan of some of the scientists who built it. Yet there it was, drifting silently in the cold void between the stars, its golden record still attached, a time capsule bearing the sounds, images, and greetings of Earth, meant for any intelligent life that might someday encounter it. Voyager 1's journey serves as a powerful reminder of human